Good morning, all of you. The power diode was the semiconductor device which we were discussing about in the last lecture. Since it happens to be the most fundamental device among all the semiconductor devices, and the basic device among all the semiconductor devices which are expected to be studied when we are discussing with the power electronic semiconductor devices. So we have compared power diode and the signal diode yesterday. That is how and in which sense the signal diodes or the ordinary diode and power diode they are differ from each other. Signal diode, in another word, it is also called as p-n junction diode. We simply say it as a p-n junction because the fundamental building block of any diode is a p-n junction. So we call it as a p-n junction diode because the existence of diode is because of the existence of the junction between p type of semiconducting material and n type of semiconducting material. So when they are exposed to each other, suppose they are connected at the surface, where at the one side there is a p type of material and at the other side there is n type of material. When they are connected with each other, there is a diffusion of electrons from n region to p region and holes from p region to n region. So they will enter, and at the junction they will form a layer to which we refer as a p-n junction, or at the surface they will form the p-n junction. So due to the diffusion of electrons and holes from both the sides, there is a band to which we call as a p-n junction, and after some time it is impossible for electrons to enter in p region and holes in n region, so they will stop diffusing. The moment they will stop diffusing, it is not possible for electrons to enter in p region and holes to enter in n region because of the potential barrier across this layer, across this p-n junction. So it is quite difficult for normal electrons and holes to cross that potential barrier, and that's why we doesn't get current conduction from p to n normally when the diode is not connected in a circuit. Diode is not connected in the circuit, the meaning is that diode is unbiased. There is no biasing applied. Now, how can we apply bias? Or what is the significance of applying bias? Or why we are applying the force from P and N region so that there will be current conduction? It is because the potential barrier here. Because to get the normal current from P to N, as we say, we need to apply some external force. We say we are applying EMF. So the process of applying EMF, we call it as a biasing. Okay. Now, while applying biasing or EMF, we connect P side of this junction to N lead or P lead, means positive of EMF. Okay, positive terminal of EMF, and the N lead or N terminal or N part of that PN junction, we are connecting it to the negative terminal of the EMF which we are applying, by which we are providing the bias to the diode. Then it is possible for holes as well as the electrons to enter in P region and N region respectively. Okay, generally we say there is no such a called positive holes. There is an appearance only. These are imaginary charges, but the electrons, they do have charge, electron charge. So what actually flows, or which charge actually flows, is electronic charge. So there is a flow of electron from N to P, and we assume the conventional current direction opposite to the electron current. So we get the normal current from P to N. So we say the diode is in forward bias. So while applying bias, when we connect the PN junction in this fashion, then we say the diode is in forward bias. So this is what is the normal operation of the diode. This is the general concept associated with the diode. Any diode, let it be signal diode or let it be power diode. Okay, that is to make them conduct, we need to apply biasing. We need to apply EMF. So when we put them in a forward bias, we get this normal current. The another way of biasing is reverse bias. That is not expected for normal operation. Okay. In reverse bias, what generally we do? We connect P side of PN junction to the negative terminal of EMF and N side to the positive terminal of EMF. That is the vice versa of forward bias. So in that case, we'll get the reverse current, which is called as reverse current or the backward current. Okay, so this is what is the reverse bias. But which biasing normally expected? We are expecting the forward bias. Any diode should be in a forward bias for its normal operation. Okay, so this happens with any diode, let it be signal diode or the power diode. Okay, now in case of power diode, we say by applying biasing, what we are doing, we are making this diode to conduct. When a power diode is applied with the forward bias, the current carried by that diode, that is power diode, is in terms of kiloampere. In terms of kiloampere. Okay, and the current carried by the signal diode, it is maybe in milliampere or just normal ampere, very small current. So this is what is the difference between signal diode and power diode. The forward current carried by power diode is very high as compared to the signal diode. Okay, but the process remains same. What do you mean by process? To make the diode conduct, let it be signal diode and power diode, we need to apply biasing. We need to put them in a forward bias. Okay, same is case of reverse bias. Suppose when we connect the diode in reverse bias, let it be signal or ordinary diode, when we connect it in a reverse bias, it will block the forward voltage or it will block the voltage. So the amount of voltage or the quantity of voltage, okay, blocked by the signal diode is very less. That is very less. You can say only volts or millivolts in case of signal diode. But when power diode is connected in the reverse bias, the amount of voltage blocked by reverse bias power diode is very high. That is in terms of kilovolts. Okay. So this is what is the difference between signal diode and power diode. That is, the rating of current in forward bias is very high and rating of the voltage in reverse bias is very high. This is the current conducted by power diode in forward bias and this is the voltage blocked by power diode in reverse bias. So the significance of voltage and current in forward bias and reverse bias. For current, there is a scope of forward bias. Means in forward bias, we need current. What is the current? And in reverse bias, what we need? What is the blocking voltage? Reverse blocking voltage. So current is optional or current has not given that priority. In forward bias, current is given priority. Voltage doesn't matter. Okay. In reverse bias, voltage is given priority. Current doesn't matter. Okay. So that is the difference between forward bias and reverse bias, or the importance of forward bias and reverse bias. But in both the cases, the common thing is bias, because we can operate given diode in any circuit only if we are biasing them. Okay, if we are keeping them unbiased, means that is the normal semiconductor device. It has no role in that circuit. Okay, so for that we need to apply the bias. Are you getting my point? So this is what is the difference between signal diode and power diode. Now, as I mentioned, the fundamental building block of any diode, let it be power diode or signal diode, is a PN junction. Okay, every diode has one PN junction. Okay, two terminals, that is anode and cathode. Okay, and two types of material, P and N. Two terminals. Okay, two terminals, anode and cathode. Two type of the semiconducting material, P type and N type, and one PN junction. Okay, these are the characteristics, or these are the features of any diode, let it be signal or let it be power diode. But power diode is little bit different in the structure and in the configuration if we compare it with the normal diode. सिग्नल डायोड आणि पॉवर डायोड यांच्या स्ट्रक्चर मध्ये थोडा फरक आहे. आता सिग्नल डायोड तुम्ही बघू शकता या ठिकाणी एका बाजूला पी टाइप आहे, एका बाजूला एन आहे, दोघांच्या मध्ये काय आहे, पीएन जंक्शन आहे. If we look at the structure of power diode, it will have these many things associated with it. जर आपण पॉवर डायोडचं स्ट्रक्चर बघितलं तर या पद्धतीने ते कॉन्फिगर केलेलं आहे. इथं बघू शकता तुम्ही एनोड आणि कॅथोड. नॉर्मली दे आर हॅविंग it is having two terminals. In short, we call it as A and K. Okay, these are the two terminals, which is very common as same as that of signal diode. But if we look at the layers it has in the structure of power diode, they are completely different. We have the first layer, to which we call as a cathode substrate. Now, since N type of semiconducting material represents cathode, okay, so it is to the side of cathode. What? Cathode substrate. That is, this is the fundamental or the basic material for the cathode. The lead which we are connecting it to the N type of material, we call it as a cathode. So to form cathode, what we need is a cathode substrate. So you may say this is N type of silicon, N type of silicon. And if you look at this part, which is anode substrate, which is shown by blue holes here, which are nothing but anode substrate. Now, this is the representation of holes. That's why I have shown this with the small circles. So what is this? This only part belongs to anode substrate. Okay. And in between anode substrate and cathode substrate, there is a scope for N substrate to grow towards anode substrate. Then and then only we can say that there is a flow of current conduction. That is, there is a possibility of recombination of these materials. So for recombination, there should be mobility of electrons. Okay, we normally say when electron flows, the current flows, and that's why we need to give enough scope for the electrons to grow towards anode, and that's why there are different layers from cathode substrate to anode substrate, and these layers are growing in nature when actually these devices are put in a conduction, and that's why that particular region is called as drift region. You can say here the region showed with the slanted line, it is a drift region, and this black dots, this region, it is the scope for drift region to grow epitaxially. So this layer is called as epitaxial layer of N substrate. Okay, so this is cathode substrate, this is the drift region in which cathode substrate will grow epitaxially, and this is the anode substrate. There is no meaning of growing anode substrate towards the cathode, but cathode itself will grow towards the anode substrate. Okay, that is the natural behavior of cathode substrate to grow towards the anode substrate. Because normally when we define the current, we say that the electrons are flowing. So we call it as a mobility of electrons. There is a less scope for mobility of holes. And that's why we need to mention that what is growing, cathode substrate is growing epitaxially in this region. So there is a scope for drift cathode substrate to grow in this region, and that's why it is called as a drift region. Drift means just moving one above the other. That is called as drifting. Okay? If you go by meaning of the word, it will grow. Okay? It will grow towards the cathode substrate. And the moment it will grow in very high density, we say that there is a electron current from cathode to anode. Okay? And if there is an electron current from cathode to anode, we say there is a normal current from anode to cathode. So which current we are expecting here? Forward current of power diode. Now what is the forward current of power diode? It is opposite to that of electron current. So expected current must be from anode to cathode because it is opposite to the electron current. Okay, so this is how the mobility of the electron will take part in the current conduction. So in fact, the mobility of the electron is the reason behind why the devices are in a conduction. Okay, so this much things or these things are not included when we consider the signal diode. This is the part of power diode. Okay, it is because the current rating and the voltage rating which is handled by the power diodes. So the power diode need to be given scope for these things in the structure. That is, it should have cathode substrate. It should have enough scope for drift region to grow epitaxially towards the cathode substrate, towards the anode substrate. Then there will be anode substrate. Then above the anode substrate, as an external part, we need to connect this terminal, the anode substrate, to the positive of biasing which we are applying. And for that, we need to have anode metallization. So this is the metallic part to which we are connecting the positive terminal of biasing. Okay, and this is also this complete shaded part. It is the cathode metallization, which is connected to the negative terminal of the bias. Okay, here simply I have shown these two half circles of semicircles here to connect them to the positive terminal and negative terminal. But here I need to provide them with the metal part. So metallic part is present, anode metallization, cathode metallization. Okay, so we should identify, or we should realize that we need to put in a cathode metallization and an anode metallization. The reason behind this is the ratings with which the power diode is associated. It is very high. The current is very high in terms of kiloampere. The voltage is very high in terms of kilovolts. So kiloampere, when the diode conducts normally, power diode conducts normally, very huge current flows from anode to cathode. Okay, and when we put this power diode in reverse bias, very huge voltage will be blocked by this power diode, and that voltage in terms of kilovolt. Okay, so in forward bias we get the expected forward current, and in reverse bias we get the forward reverse blocking voltage. Okay, actually we block the voltage when we connect this diode in a reverse bias. Okay, what is the point to remember from the structure of the signal diode and power diode is, in power diode we need to think of different concepts. The concept like what is cathode substrate, what is the role of cathode substrate, then what is the significance of drift region. Okay, how it will grow. It will grow like epitaxial growth. Okay, then we have anode substrate, and the region across which the anode substrate is distributed is less as compared to cathode substrate. Since we need to think of electron mobility, So there should be high priority to the electron mobility. And that's why cathode substrate region wise is more. Okay. If, if you look at this cathode metallization also, this is across the complete surface of that power diode, cathode metallization. But anode metallization is just limited here. Okay, so anode has little scope, anode substrate has little scope, but cathode substrate has more scope in the structure of power diode that we can identify by observation itself. Okay, but see that this is the part of N material only. What will grow is N material, but that growing is like epitaxial and the behavior is different. Here in this part, the cathode substrate will behave like normal cathode substrate, that is N type of silicon material or N type of semiconducting material. But here in this region, the behavior of this N substrate will be completely different. It will be more likely towards moving towards the anode substrate here in this part. So this type of growing of cathode substrate, we call it as epitaxial growth. Epitaxial growth. Okay. So this is how is the structure of power. And when we are supposed to plot the characteristics in the next part of this power diode has two types of characteristic. One, it is VI characteristic. Means what? How voltage and current behaves with respect to each other during the conduction of forward current from anode to cathode. How current will behave with respect to voltage. Voltage means uh, the current conduction will be monitored by voltage across anode to cathode. So what happens with the current if we change the voltage? That is VI characteristics of power diode. The another type of characteristic is reverse recovery characteristic. So we will see that in a detail. Okay, what is the nature of VI characteristic? How we can plot those characteristics? Okay, and then what is the nature of reverse recovery characteristic and what is importance of those reverse recovery characteristics? How we get those characteristics? Okay, so this is, I guess, understanding of the structure of normal diode, signal diode, and the structure of power diode is very important before we discuss the characteristics of power diode. Okay. So let me start with the presentation where we were interrupted in the last lecture. Okay. For that, I'll stop. Okay, I'll directly share my screen. I'm expecting all of you to draw whatever I have drawn on the board in your notebook. Obviously, I'll be sharing presentation, material, everything with you. But simultaneously, during conduction of this class or the lecture, you need to draw and you need to take down the important points. You have freedom to use the best suitable material, study material, which you can get from any source, maybe on the internet or maybe from your friend or any reference book or textbook that you are using. But as a complementary, you can use your notes which you have prepared during class. think this was the point. So diodes are the simplest semiconductor devices. As I said, this is one of the fundamental semiconductor device. Has one PN junction, two terminals, and two layers. So P and N, as well as two terminals, anode, cathode. Okay, and one junction are the part of PN junction diode. The ordinary signal diodes have a junction formed by P type of semiconductor and N type of semiconductor material. The lead joining P type is called anode, where the N type we call it as a cathode. That we know. Okay, so this is what is the structure of signal diode. The figure below depicts the structure of signal diode and its symbol. So normally we draw the symbol of cathode like this. Okay. Yesterday I asked, and in the last week itself, during my practical session, what is the symbol of power diode? And means I cannot share my opinion here. The way they draw the signal of power diode, the student of third year, and that too electrical engineering student, which have studied the basic electrical fundamentals of electronics engineering and then analog electronics as well. Signal diode has the symbol showing anode and cathode like this. Power diodes are similar to the signal diode, but have little difference in its construction, that is in the structure. मी जे तुम्हाला मगाशी आता ड्रॉ करून सांगितलं किंवा एक्सप्लेन करून सांगितलेलं आहे त्यांच्या स्ट्रक्चर मध्ये फरक आहे. ठीक आहे, कारण सिग्नल डायोडच्या स्ट्रक्चर मध्ये एनोड सबस्ट्रेट ड्रिफ्ट रिजनला काही स्कोप नाहीये. ओके, त्याच्यानंतर पॉवर डायोड्स आर meant to conduct the current up to several kilo amperes when they are connected in the forward bias and to block the voltage up to the kilovolts in the reverse bias. So two type of biasing we are applying for the power diode. One is forward bias and another is reverse bias. So during forward bias the current is important and that current is very high. In case of power diode, that current is very high, and when it is in the reverse bias the voltage is very high. The voltage blocked by the power diode is very high. So that is the difference between signal and power diode. In signal diode, doping level of P and N side is the same and hence we get PN junction. But in power diode, we have junction formed between heavily doped P plus and lightly doped N minus layer, which is epitaxial grown on heavily doped N plus layer. Okay. Now, somewhere I need to show this where you are you have shown in the structure of cathode substrate. Here you need to show cathode N plus. That plus sign doesn't mean it is charge. It means that it is heavily doped. Because while doping of the semiconducting material, we say there are two methods. The process is called doping, and there are two types of doping. One is heavily doped and another is lightly doped. So meaning of N on its head plus. N plus doesn't mean that N positive. N plus means that N type of semiconducting material is heavily doped, and when it is N minus, then we say that N type of semiconducting material is lightly doped. Okay, so in power diode, a junction is formed between heavily doped P plus and lightly doped N minus layer, which is epitaxially grown on a heavily doped N plus layer. Okay, heavily doped N layer. Okay, so this structure we already studied. You can observe there N plus, and in the drift region you can mention drift region the N minus. N minus, the meaning is that in the drift region cathode substrate is lightly doped. Okay, it will grow like lightly doped N substrate or cathode substrate towards anode substrate, okay, which is heavily doped. So how will you isolate these layers? P plus heavily doped anode substrate, N minus lightly doped cathode substrate in a drift region, and then N plus heavily doped cathode substrate. Okay, these are the layers of this structure in the power diode. So the N layer is the key feature of the power diode, which makes it suitable for high power applications. Okay, so the existence of this drift region that is lightly doped cathode substrate is responsible for very high power handling capability of the power diode. Okay, that is in terms of voltage and current. Power handling capability is nothing but handling voltage and current, which is very high. What is the reason behind that? The reason is the presence or the existence of that drift region, as I told you. So drift region represents lightly doped cathode substrate N minus. Okay, that is the reason behind power handling capability of power diode, which is very high. Okay. So the layer is lightly doped, almost intrinsic, and hence the device is also known as pin diode. Sometimes power diode are also known to be pin diode, PIN. PIN. Pin याचा अर्थ P stands for PN junction मतलब P. N stands for PN junction मतलब N. And I stands for intrinsic. Okay. So intrinsic, the lightly doped, almost intrinsic, and hence the device is known as pin diode, where I stands for intrinsic. As we can see in the figure above, that is the structure of the power semiconductor device, power diode, that the net charge neutrality of the space charge region is still maintained as was in case of signal diode, but the thickness of the space charge region is quite high and deeply penetrated into lightly doped N region. Okay, because as I mentioned, that we need to give enough scope to grow epitaxially to the cathode substrate, and for growing that, we can say we should give enough space for lightly doped cathode substrate. Okay, that is the reason why we have shown the area which is covered by drift region is much more as compared to the cathode substrate and anode substrate. Okay? In fact, anode substrate is occupying very less space across the structure of power semiconductor device or the power diode. Okay? It is occupying very less space. But drift region has enough scope to increase in its space epitaxially. Okay? Next. This is due to the light doping concentration. This slide is continued. As we know that the thickness of the space charge region increases with the decreasing doping concentration. Okay. This increases the thickness of depletion region on the space charge region, helps the diode to block the larger reverse bias voltage and hence have a greater breakover voltage or breakdown voltage. Okay. This is the reason why we get the very high breakdown voltage across the power diode when it is connected in the reverse bias. As I mentioned, it has correlation with this concept where there is a lot of space for the charge region, okay, space charge region. However, adding lightly doped N layer significantly increases the ohmic resistance of the diode, leading to more heat generation during the forward conduction state. Yesterday only we see that we have seen that the heat dissipation, the amount of heat dissipated is very high, and that's why the power diode they do require the heat sinks to be connected. The reason is that this, because it has a lot of scope for the drift region and because of which the resistance offered by this end region for the flow of current from anode to cathode, that is forward current, is very high. So if there is a resistance inside, internal resistance of the semiconductor, then there is a heat dissipation. Okay, and that heat will be sink by the heat sink which we are providing along with the power diode. So that is the requirement of power diode. If we are placing power diode on the circuit board, and if the voltage and current ratings are high, in that case we must employ heat sink along with the power diode. Without heat sink, your circuit will get damaged because of heat dissipation. Okay, so hence power diode comes with the various mounting of proper heat dissipation assembly or proper heat dissipation arrangement. Okay, is there along with the power diode. म्हणजे पॉवर डायोड हा नेहमी हीट सिंक सोबतच जोडला जातो. याचं रिझन आहे हीट डिसिपेशन. हीट का होते तयार, कारण एंड रिजन मोठा येतो आणि एंड रिजन काय करतो, फॉरवर्ड करंटच्या कंडक्शनला अपोज करतो आणि करंट कंडक्शनला अपोज झाला की कन्सिडरेबली हाय हीट तयार होते की ज्या हीटला सिलिकॉन मटेरियल विथस्टँड करू शकत नाही, कारण एक लिमिट आहे हीट ऍब्झॉर्ब करण्याचं. त्याच्यावरती सेमीकंडक्टिंग मटेरियल काय होतं की जे मॅन्युफॅक्चरिंगसाठी पॉवर डायोडच्या वापरलेलं आहे ते काय होतं, डॅमेज होतं. ओके, सो टू प्रोटेक्ट अँड टू get rid out of that heat dissipated during the forward conduction, we need to employ the heat sink along with the power diode. Okay, generally the appearance of power diode will be like this. सिम्बॉल आपण ड्रॉ करतोय तो पॉवर डायोड नाही आहे जो आपल्याला दिसतो. आपल्याला पॉवर डायोड हा या पद्धतीचा दिसतो, जो मी या स्लाइड मध्ये दाखवलेला आहे. अशा पद्धतीचा जर डिव्हाइस तुम्हाला दिसला तर तो काय आहे, पॉवर डायोड आहे. ओके, then VI characteristics of power diode. As I mentioned that the characteristics are very important and they plays vital role in case of power semiconductor devices. This is the very first characteristic we are studying, and that to the fundamental semiconductor device like power diode. Okay, from here onwards there will be different semiconducting devices, semiconductor devices to which there are different characteristics associated. Now for power diode, as I mentioned, we have two types of characteristics. One is VI characteristic and another is reverse recovery characteristic. So out of that we'll discuss now the VI characteristics of power diode. So how these characteristics can be derived and can be plotted, we'll see. Okay, in signal diode for power forward bias region, the current increases exponentially. However, in a power diode, high forward current leads to a very high ohmic drop, which dominates the exponential growth, and the curve increases almost linearly. So, during initial part of the characteristic, there is a linear relation between voltage and current in the initial part. Now, what happens if this procedure continues? Okay, the maximum reverse voltage that the diode can withstand is depicted by reverse recovery maximum voltage, that is VRRM, that is peak reverse repetitive voltage, peak reverse repetitive voltage. Okay, RRM, that is the maximum voltage. Above this voltage, the reverse current becomes very high abruptly, and as the diode is not designed to dissipate such a high amount of heat, it may get destroyed. This voltage may also be called as peak inverse voltage. So this is one more parameter which is associated with the power diode, peak inverse voltage. Peak inverse voltage we generally get when diode is connected in the reverse bias. Okay, so the reverse current becomes very high. The moment at which the reverse current becomes very high, there is a possibility of breakdown of that junction, PN junction. Okay, because of which actually we get the very high reverse current, and when it gets breakdown, there is a possibility of destruction of the device because of the heat dissipated. And the voltage at which it happens, the voltage at which generally the junction breaks, we call it as a peak inverse voltage. Or it is the voltage, the maximum voltage that we can apply to the reverse bias power diode when it is connected. The maximum voltage withstand by that diode is a peak inverse voltage. Okay, above that voltage, there will not be the normal device. So there will be breakdown of that PN junction and the device itself. Okay, so peak inverse voltage we get it when we connect the power diode in the reverse bias. So this is how is the nature of VI characteristic. As I mentioned in the first quadrant, you need to plot voltage on x-axis where current on y-axis generally for VI characteristic of the power diode. So in the first quadrant, you'll see that the diode is connected in the forward bias. So the normally current increases with the increase in the voltage. But if you look at the current, how it is increasing? It is increasing exponentially. Okay, so there is an exponential graph between voltage and current. There is exponential relation between voltage and current. By observation, you can say that if we change voltage by very small magnitude, the current will increase abruptly. At some particular instant, the current will become very high. Okay. So the first quadrant operation we get because of forward bias connection of the power diode. When power diode is connected in the forward bias, means P type of or the anode is connected to the positive terminal and cathode is connected to the negative terminal. This is the normal operation of power diode, because of which we get the normal current as expected, normal forward current as expected in the first quadrant of VI characteristic. But if we reverse the connection, that is, if we put power diode in the reverse bias, what happens with that? We generally get very little current. The current, if you look at the current, even if you go on increasing the voltage, still you go on increasing the voltage, but there is a no reverse current, very small reverse current, that too because of minority carriers. See, when we get current in the forward direction, when it is connected in the forward bias, we get the current because of majority carriers. Okay, and when we connect power diode in the reverse bias, we get the current because of minority carriers. This is another concept, okay, of forward bias and reverse bias diode. But if we still go on increasing the reverse voltage across the power diode in reverse bias condition, if we are increasing the negative voltage or voltage across the power diode, the moment will reach where the current will become very high. Current will abruptly increase. Earlier it was very less, very small, negligible current because of minority carriers. But when that limit overs, the limit crosses above generally the peak inverse voltage, what happens? The current will start to increase abruptly. Okay, so we'll get the reverse current, and the voltage at which we get this very high current or above the voltage, that limit of the voltage, we call it as a peak inverse voltage. And till the current which is flowing when it is in the reverse bias, we call it as a reverse leakage current. Leakage, the meaning is very less current flows up to peak inverse voltage. But above peak inverse voltage, we say only reverse current, not leakage current. Because leakage current is due to the minority carriers, and it is very less as compared to the normal current. Hence, it is referred as a leakage current. But above peak inverse voltage, what happens? The current increases very abruptly. So that current will always be very high, and it will not be called as a leakage current, but it will only be called as a reverse current. Okay? म्हणजे करंटला कुठपर्यंत लिकेज म्हणायचं, जोपर्यंत ब्रेकडाऊन होत नाही तोपर्यंत. ब्रेकडाऊन नंतर मात्र करंट जो असतो तो काय असतो, मोठा असतो, आणि त्याला काय म्हणतात तुम्ही, नॉर्मल रिव्हर्स करंट. आणि ब्रेकडाऊन पर्यंतचा जो करंट आहे तो लिकेज करंट. लिकेज करंट इज द रिझल्टंट ऑफ रिझल्टंट ऑफ मायनॉरिटी कॅरीज, okay, in the reverse bias condition. So this is the nature of VI characteristics we get across the power diode. Okay, these characteristics can be represented in terms of this expression ID. ID stands for forward diode current, anode to cathode, is equals to IS. IS stands for reverse leakage current into e raised to Vd divided by eta Vt minus 1. So from this expression, what you can conclude? The relation between the current and voltage is exponential. E raised to x, y is equals to e raised to x. Here x is voltage. Okay, we normally write exponential equation like y is equals to e raised to x. Y here is current that you can observe on y-axis. E raised to x, x is a voltage that you can observe on x-axis. Okay, so current is on y-axis and voltage is on x-axis. That is the relation between voltage and current is exponential. That is how we need to understand the relation between voltage and current in power diode, and we can conclude that the relation is exponential in nature normally. Okay, so that is the end of today's session. So we have seen in this particular session the operation of power diode and signal diode, difference between them, the structure of power diode, how the structure of power diode differs from signal diode, and then we have seen the VI characteristics of the power diode. Okay, these are the important points which we covered in today's session. I hope you are writing and drawing the diagrams in your notebook. So